Everybody. Today we are discussing the next topic, that is the polarography. Polarography is an electroanalytical method in which the change of the current from the electrolysis of the analyte solution containing reducible and oxidizable analyte are followed by a polarizable microelectrode. Usually we are using the dropping mercury electrode and a gradually increasing applied voltage. And here there are two electrode normally. One is the reference electrode. Usually we are using the calomel electrode as the reference electrode, and the second electrode, that is known as the indicator electrode or working electrode. Usually we are using the dropping mercury electrode as a working electrode or a indicator electrode. You know that the dropping mercury electrode is a polarizable electrode. That means if you are applying a voltage, the electrode cannot acquire that voltage properly. So there is a slight variation in the potential of the dropping mercury electrode. So this type of the electrode is known as a polarizable electrode. So in order to acquire the amount of the potential which is acquired in the polarizable electrode, we are using another electrode, that is the counter electrode. Now this is the simple setup of the polarography, and a fine capillary glass tube is connected to a bulb which containing a mercury, and which are constantly renew, and which will drop out the mercury droplet which is acting as a the electrode, and constantly which is renewed, and ideally fresh and very clear and smooth surface is acquired for each dropping mercury, and we can use even in a small volume. That is the speciality of the dropping mercury electrode. Now this is the simple setup for the polarography. Now we are using the supporting electrolyte here for the analysis. The role of the supporting electrolyte is that which are used for practically eliminating the migration current. And migration current means uh, migration current which is eliminate the migration of the charged particle in the electric field by a potential difference existing between the electrode surface and the solution. And migration current is carried out by the ion of the supporting electrolyte and the analyte species to follow the diffusion transport. And this is the curve of the polarography, the sigmoid curve. And if we are applying the potential, the current is usually increases, and polarography is usually uh, representing the voltage in the x-axis and current in the y-axis. So polaragram is naturally, it is a relationship between the voltage and the current. And initially if you are charging the dropping mercury electrode, we have a potential difference is existing, that is the residual current. And while taking the reduction or the oxidation of the material in an analyte solution, it will produce a diffusion current. And after that, while we are charging the while we are applying the voltage, the potential current is increases in a steady manner. That is the polaragram. So and we know that the ID current or the diffusion current is the difference between the residual current and the limiting current, and from that we can identify the material. And the polarography have several applications. These are the some of the application of the polarography. And this is the equation which operate the polarography, that is the Ecowick equation. This equation is very important. And next is the half-life potential and its significance. From the half wave potential we can identify the material, and from the height we can measure the quantity of the material which is present in the analyte solution. These are the basic principle of the polarography. Now we are moving into the limitation of the conventional polarography. So one of the advantage is that it determines the concentration of the organic and even inorganic analyte solution. But every method have some of the limitations. So similarly, this conventional polarography has some limitation. One is it can be used to the detection of the ions even in the range of the 10 to the power minus 3 to 10 to the power minus 4 molar. And the dropping mercury, the drop time of the mercury is only 2 to 3 second, 2 to 8 second. So the DC potential is applied to the dropping mercury electrode and corresponding current is recorded in a continuous manner. So we cannot easily identify the material. So that is one of the drawback. And the last one is the lack of the resolution of the sigmoid shaped wave. So these are the different limitations of the conventional polarography. So in order to overcome these limitations, we have several other methods, that is the pulse polarography, differential pulse polarography, AC polarography. These are some of the method which is used in the modern polarographies. So pulse polarography means the potential is applied in the form of a pulse, and we can use the two different type of the pulse. One is normal pulse polarography, the second one is the differential pulse polarography. In the normal pulse polarography, a rectangular polarigram is sigmoid type, but it is of the staircase type, and a pulse is applied for every 50 milliseconds, and but current recorded for 70 milliseconds. So in the pulse polarography, see here, the potential, see the potential ramp, the potential is applied normally, which is in the increase mode. But as in the case of a linear sweep means that is the classical polarography. In the classical polarography, see the top one, the potential is applied in a steady manner, and which is in an increasing mode, and that is a linear mode. But in the pulse polarography, we are applying the potential or the voltage in a square type, and we are measuring the value in the uh, before the dropping and after the dropping, and we will get a sigmoid curve, but the resolution of the sigmoid curve is very high. So that is the advantage. And the constant base is a potential is applied to the dropping mercury electrode, and which can the capability to dictate the concentration even below 10 to the power minus 8 molar. So this is the pulse polarography, and instead of linear charge, as we said earlier, we are applying the staircase type pulse, and we have to measure the potential at the two cycles, even first in the application of the first pulse, and the second one is in the end of this square. So we can convert it into a signal, so we can easily detect the position, and properly we can resolve, or properly we can identify the concentration. So next is the differential pulse polarography. So continuously increasing the DC potential imposed with a pulse constant amplitude. See here in the differential pulse polarography, we are giving the potential which is in a increasing order, whereas in the case of the pulse polarography, we are applying the steady, but it is a square type manner. But here we are applying the constant pulse, but that is an increasing order. So see the potential, and here we can obtain the instead of sigmoid curve, we can obtain the peak directly. So from the peak we can identify the material, and from the peak height we can identify the concentration. So continuously increasing the DC potential is the superimposed with the pulse of the constant amplitude, and the pulse is applied only at the end of the drop for the 50 milliseconds, and current is measured twice during each drop, and before the application of the pulse and at the end of the pulse, and the difference between these two curves is plotted as a function of the baseline potential. So polarigram consisting of a peak instead of the sigmoid curve. So these are the difference between the pulse and differential pulse polarography. One of the advantages is that non-Faradic current, that is residual current, can be eliminated here. That must be zero. So the total current is recorded at end of the pulse is only the diffusion current, and we can dictate the concentration even at the 10 to the power 8 molar concentration. And advantage of the alternating current AC polarography, the surface concentration charge is a response to AC potential. So in the pulse and differential pulse polarography we are applying the DC current, whereas in the alternating current we are applying the AC current. So there are two type of the current generated at the dropomercury electrode. The total current is the resultant of DC and AC curve. Okay, so the advantage is that we can dictate even in the 10 to the power 8 and no need of the pumping the nitrogen gas, mm, which is used for removing the oxygen. Okay, this is the square wave polarography, and the square wave polarography is more sensitive and much faster than the differential pulse polarography, and the square wave is also better at rejecting the background signal as those generated by the reduction of the oxygen. So we will get a clear picture about the reaction. Okay, thank you.